188 tons of Krupp forged steel. The Panzer VIII Maus was not defeated by the piercing kinetic energy of Allied artillery, nor was it shattered by aerial bombardment. This mechanical Leviathan was ultimately executed by the very earth it attempted to conquer. Let us strip away the propaganda and execute a complete digital teardown of the heaviest armored vehicle in human history. Initiate the Boolean cross-section cut on the outer hull. We are mathematically peeling back the 100mm thick lower side armor to expose the dynamic mechanical nightmare hidden beneath. Look directly at this massive track assembly. Each track link is 1.1 meters wide. This forges a gargantuan footprint that was physically doomed from the exact moment Ferdinand Porsche presented the blueprints to Adolf Hitler. Zoom in on the internal suspension system. We are isolating the double-volute spring bogies, specifically designed by Skoda to carry an impossible burden. Notice the sheer molecular density of the cast steel housing surrounding the road wheels. When 188 tons of dead weight bear down on these specific axles, the torsional strain reaches catastrophic levels. This pushes the chromium molybdenum steel right to its ultimate tensile strength limit. Imagine balancing a fully furnished 4-story concrete apartment building on top of a single commercial bulldozer track. That is the exact vertical shear stress being applied to the ground below this machine. The theoretical ground pressure was listed at 1.45 kilograms per square centimeter. This is a deceptive number that completely ignores the aggressive dynamic load generated when this Leviathan actually attempts to move. The moment the primary drive sprockets engage the tracks, the immense mechanical vibration combined with the staggering vertical force instantly shatters the structural integrity of the topsoil. We are talking about immediate, localized soil liquefaction. The earth beneath the Maus ceases to act as a solid, weight-bearing surface. It instantly transforms into a highly viscous, inescapable fluid. This effectively swallows the lower chassis millimeter by rolling millimeter. Now, let us shift our three-dimensional rendering probe deeper into the rear engine bay. We are making the 200mm thick frontal glacis plate completely transparent. Hidden behind this impenetrable wall of solid rolled homogeneous armor lies the beating heart of this thermodynamic disaster. Behold the Daimler-Benz MB509 V12 aircraft engine. This was later replaced by the MB517 diesel, coupled directly to a massive Siemens-Schuckert electrical generator. This is the infamous Porsche hybrid electric drive system. Observe the physical clearance around the engine block, or rather, the absolute lack of it. The power plant is hermetically sealed within a claustrophobic steel tomb. Now let us run a full simulation of the thermal output under combat load. Activate the infrared heat map overlay on our digital model. The massive 12 cylinders fire in rapid succession, attempting to generate 1,080 horsepower just to overcome the static inertia of the vehicle. The thermodynamic waste heat has absolutely nowhere to escape. The ambient temperature inside this sealed engine compartment spikes exponentially within minutes. This essentially transforms the rear section of the hull into a pressurized rolling blast furnace. The massive copper coils of the internal electric traction motors begin to physically degrade under the extreme thermal stress. This increases electrical resistance and further bleeds engine efficiency. The heavily armored crew compartment, positioned dangerously close to this unvented thermal anomaly, begins to rapidly bake. The mechanics and drivers are not merely operating a heavy tank. They are trapped inside a mobile crematorium surrounded by high explosive ammunition. Let us strip away the outer casing of the Siemens Schuckert electric traction motors located in the rear drive sprockets. Notice the intricate winding of the stator and rotor coils. In a standard industrial application, these motors require massive external cooling towers to dissipate the heat generated by the electrical resistance. Inside the Maus, they are cooled by a desperate undersized internal fan system. This simply churns the already superheated air around the engine bay. When the driver attempts to pivot this behemoth on soft ground, the electrical current spiking through these coils reaches critical amperage. The copper wiring physically expands, the insulation melts, and the risk of a catastrophic electrical fire becomes a statistical certainty. We are watching a machine that is perpetually on the verge of self-destruction. It is fighting a two-front war against the Allied forces outside and the laws of thermodynamics inside. Let us analyze the fluid dynamics and the resulting logistical nightmare of keeping this beast alive. The fuel consumption is not just inefficient, it is a mathematical absurdity. The Maus demands a staggering 3,800 liters of high-octane fuel for every 100 kilometers traversed in optimal conditions. To put that sheer volume into a physical perspective, listen closely. This single tank consumes enough refined petroleum to keep an entire squadron of Messerschmitt Bf 109 fighter planes airborne and fighting for hours. And that is just to crawl at a pathetic 13 kilometers per hour on a perfectly paved, reinforced road. And the Eastern Front in 1945 did not have paved roads. It had deep, unforgiving mud. Disconnect the primary drive shafts in our digital model and look at the electrical cables connecting the generator to the rear drive sprockets. Porsche engineered a system that bypassed mechanical transmissions because no conventional gearbox on Earth could handle the sheer torque required. Moving 188 tons would instantly shatter internal gear teeth into metallic shrapnel. But this electrical workaround introduced a fatal vulnerability. The electrical systems were incredibly sensitive to moisture, mud, and the extreme kinetic shock waves of nearby artillery impacts. A single fractured coolant line or a short circuit in the primary generator coil would be devastating. It would instantly turn this unstoppable fortress into a static steel bunker, entirely paralyzed on the battlefield. We are dealing with a vehicle born from the absolute extreme of dictatorial megalomania. Core engineering principles were violently sacrificed at the altar of raw, uncompromising armor thickness. Every single millimeter of Krupp steel added to the turret meant exponentially more stress on the suspension. It meant more heat in the engine bay and a faster sinking rate into the European soil. The Maus was not a tank. It was a fundamental violation of the laws of physics. A machine that mathematically consumed its own structural integrity just by existing in a state of idle. Let us transition our three-dimensional simulation from the sterile testing hangar directly into the brutal, unforgiving topographical reality of the Eastern Front. We are placing the Maus on a digitally recreated battlefield, representing the saturated, muddy terrain of 1945. As the driver engages the electric drive, the massive tracks begin to rotate. Watch the interaction between the hardened steel track links and the earth. This is where the physics of sinking truly takes over. The extreme shear stress applied by the 1.45 kilograms per square centimeter of ground pressure instantly overcomes the soil's mechanical bearing capacity. We are not seeing traction. We are witnessing rapid soil liquefaction. As the chassis sinks deeper into the mud, the belly of the hull, an expansive flat steel plate, makes direct contact with the ground. Suddenly, the Maus is no longer a tracked vehicle. It is a 188-ton steel anchor dragging across a viscous sea of mud. The localized friction coefficient along the lower hull spikes exponentially. The massive electric motors scream as they draw maximum amperage, desperately trying to overcome this immense physical resistance. Look closely at the suspension guide axles and the idler wheels. The mud acts as an incredibly dense grinding paste. It jams the complex double volute springs and snaps the hardened steel track pins under extreme torsional tension. The machine is literally tearing its own lower extremities apart, just trying to move forward. Now, we must analyze the most fatal design flaw of all: the bridge paradox. By 1945, a standard reinforced concrete or steel truss bridge in Europe was rated for a maximum load of 30, perhaps 40 tons. Driving a 188-ton Leviathan onto any structural overpass guarantees instantaneous architectural collapse. To bypass this catastrophic limitation, Ferdinand Porsche engineered an underwater river crossing system of staggering and frankly absurd complexity. We are activating the digital fluid dynamics simulation to demonstrate this procedure. Notice the massive watertight snorkel tube erected high over the commander's cupola. This was designed to supply oxygen strictly to the crew. Because the internal combustion engine cannot breathe while submerged in 8 meters of water, it must be completely shut down. The Maus must become an incredibly heavy, unguided submarine, powered entirely by a secondary electrical umbilical cable. This thick, heavy, high-voltage cable must be connected to a second Maus, remaining safely on the riverbank. The primary generator of the first tank runs at maximum revolutions per minute. It feeds high-voltage direct current through this vulnerable underwater tether to drive the electric traction motors of the submerged tank. Imagine executing this delicate, incredibly vulnerable, multi-vehicle logistical ballet while under heavy Soviet artillery fire and aerial bombardment. A single piece of shrapnel severing the umbilical cable would instantly trap the crew in a steel coffin at the bottom of a freezing river. It is a tactical and operational impossibility. Ultimately, this gargantuan machine met its end not in a glorious ground-shaking armored clash, but in a pathetic act of mechanical suicide. Let us fast forward our timeline to the dying days of the war at the Kummersdorf proving grounds. The advancing Soviet armored columns are closing in. The Maus has broken down, paralyzed by its own internal failures. The retreating German forces are forced to scuttle their own wonder weapon. Engage the X-ray thermal vision on the interior hull. See the high explosive demolition charges deliberately placed directly inside the primary ammunition stowage. They sit right next to the massive 128mm projectile warheads. We are going to initiate the detonation sequence in extreme slow motion. As the primary charges explode, they instantly trigger a catastrophic chain reaction among the stored ammunition. The initial blast wave expands outward at supersonic speeds, but it meets the 200mm thick armored walls of the hull. The hardened Krupp steel does not yield. It does not crack. Instead, it violently reflects the kinetic energy, compounding the overpressure within the perfectly sealed metallic box. The internal atmospheric pressure spikes to tens of thousands of pounds per square inch in a fraction of a millisecond. Following the strict laws of physics, this massive concentrated kinetic force seeks the path of least resistance. it travels straight upward, striking the base of the turret ring. The heavy structural bolts and internal gear teeth are sheared apart at the molecular level. The entire 55-ton turret is violently severed from its seating and thrown upward like a discarded toy. It leaves behind a shattered, burning crater of twisted metal and shattered dreams. The Panzer VIII Maus stands in history as the ultimate testament to dictatorial engineering. It is a perfect example of what happens when the psychotic pursuit of invulnerability completely ignores the fundamental laws of physics. It was a rolling thermodynamic disaster, mathematically doomed by its own staggering weight before it ever reached the battlefield. If you found this precise mechanical autopsy revealing, ensure you subscribe to DEFUNCT. We are dedicated to dissecting, analyzing, and exposing the most fundamentally flawed and fascinating machines in military history. Leave a comment below on which mechanical disaster we should tear apart next.